Lesson 3, electromagnetic force. Our guiding questions for this lecture are: how does electricity relate to magnetism? So we've talked about electricity, we've talked about magnetism. What do they have to do with each other? How can you describe the magnetic field produced by a current, so an electric current? And then what are the properties of solenoids and electromagnets? On page 258, we start with our connect it, and maybe you guys have seen one of these things before. These are found in a junkyard, usually scrapyard. Circle the magnet in the photo. How do you know that the object picking up the metal beams is a magnet? How do you know that? And then what material do you think makes up this magnet? What do you think is inside there? So if you need to pause the video for a second, pause the video and answer the question. So electromagnetic principles, electromagnetism, we're bringing these together now. Electromagnetism is the relationship between electricity and magnetism. It was found, we're going to watch this video here in a second, by this scientist early on, that electric currents actually produce magnetic fields. So we're going to watch a brief video here showing us that principle and essentially how this guy discovered this.
In 1820, Danish physicist and chemist Hans Christian Ørsted was setting up materials for a lecture. His materials included an early kind of battery called a voltaic pile, constructed of copper and zinc plates in a dilute acid solution, and a wire held in place here by a set of clamps. Ørsted and other scientists of his day knew that when a wire was connected between the positive and negative terminals of a battery, electricity would flow through that wire. Electrons actually move from negative to positive. However, the convention is to think of electrical currents as moving from positive to negative. So that's how we'll show it here, using red particles. Back then, scientists still had much to learn about electricity. Preparing for his lecture, Ørsted made a very important discovery about the phenomenon, quite accidentally. Among Ørsted's scientific paraphernalia was a compass. Its needle, of course, pointed north in alignment with the Earth's magnetic field. Ørsted happened to place the compass near his battery and was startled to notice that the compass needle moved. As Ørsted deduced, this happened because the wire produced a magnetic field around it when it carried a current. If there is no current in the wire, the needle reverts to the alignment with the Earth's magnetic field. As it turns out, an electric current, made up of moving charged particles, produces a magnetic field that circles around the moving current, as shown by these blue lines. If you reverse the direction of the current, then the magnetic field around the wire moves in the opposite direction, and the needle on the compass flips to reflect the change in field.
So say that again here. What he's saying is as electricity moves through the wire, there's actually a magnetic field around that wire. If you reverse the electrical current, you also reverse the magnetic field.
If you move the compass to a new spot near the wire, the needle will realign with the direction of the magnetic field in that particular location. Ørsted's accidental discovery was solid evidence that electricity and magnetism were related phenomena. The announcement of his findings incited a tremendous outbreak of research in the nascent field of electromagnetics in the early 1820s.
So discovered on accident. We call those serendipitous discoveries. There's actually a lot of those in science, but completely discovered on accident that electricity and magnetism have a relationship between the two of them. On page 260 in your book, Magnetism from Electricity, Predicting Phenomena. This figure shows how the direction of a current in a straight wire affects the magnetic field that forms. In the image on the left, the current flows upwards. So when I look at the picture on the left here, oops, sorry guys. Oh, that video just wants to play again. As I look at the picture on the left, I have the current moving up, and you'll notice what direction the magnetic field is moving in. This is moving counterclockwise, right? What did we just say in the video happens if you reverse the current? So if I reverse the current, what direction do you think the current's going to move in on this side? Is it going to change? So draw your predicted magnetic field lines in the image on the right. If you need a little bit of time, come back to this if you need it. So electromagnetism, and here we are once again talking about Earth, remember, in our magnetic field.
Electromagnetism, or the electromagnetic force, is one of the four fundamental forces of nature. It generates light and energy and holds atoms, matter, and the world as we know it together. Electromagnetism is a branch of physics that studies the interactions between electric and magnetic fields. All matter has an electric charge, which can be positive, negative, or zero. Opposite charges attract, while like charges repel. These electric forces bring and hold atoms together. And when atoms gain a positive or negative charge through the transfer of electrons, a measurable electric field will form. If those electrically charged particles start to move, the field will become a flowing electric current and form a magnetic field around it. Under the right circumstances, interacting electric and magnetic fields can continuously produce and sustain one another. This generates an electromagnetic field that transmits waves of electromagnetic energy or radiation into space. The intensity of this radiation is determined by its frequency. These frequencies make up what's known as the electromagnetic spectrum. Near the middle of the spectrum is visible light, such as light emitted by stars, fireflies, and computer screens. On either side are invisible electromagnetic waves. On one end are long, low-frequency radio waves that broadcast television and radio signals, microwaves that carry telephone signals and cook food, and infrared waves emitted by fires. On the other are short, high-frequency wavelengths, ultraviolet, X, and gamma radiation. Unlike low-frequency waves, these waves can pass through the human body, making them useful for medical applications. While electromagnetism has daily applications, it's also the engine that drives the planet as a whole. Thousands of miles below the Earth's surface, a layer of liquid metals churn and flow. This generates electric currents that then produce magnetic fields that all together encompass the entire planet. Called a geodynamo, this process causes Earth's poles to attain positive and negative charges, turning the planet into a giant electromagnet. This phenomenon also creates a protective layer around the planet. It shields us from the most harmful radiation in space, leaving us to enjoy a world held together by the strange and fundamental force of electromagnetism.
So magnetic fields and current. So if the current is on, so if we have electricity moving through the wire, magnetic field is also going to be on. If the current is off, on the other hand, if you have no electricity flowing, you're not going to have a magnetic field that is going. So when we look at the strength of a magnetic field, I mean, you look at this thing that's on the slide here, clearly we'll look at this and we're like, that's got to be really strong, right? Look at all of that metal it's picking up. If I want a really strong magnet, I'm going to have more current running through there, which is going to give me a stronger magnetic field. So if we're dealing with our own things, imagine if I gave you a bunch of batteries in a lab, add batteries. The more batteries you add, the more current, the stronger that magnetic field is going to be. So the direction of the field, as we just said earlier, if you reverse the current, you are going to reverse the magnetic field. So reverse the current, reverse the magnetic field. When we look at magnetic fields, they're around straight wires like you see in the picture here. The direction of the field depends upon the direction of the current. What we use is something called the right-hand rule to determine the direction. So if you look in this picture on the right-hand side here, it says imagine that you're holding the wire in your right hand with your thumb pointing in the direction the current flows. The direction of the magnetic field is the same direction that your fingers would curl around it. So look at that person's hand as they're kind of gripping that wire. You can see that's the same direction, just like down here on the bottom, that's the same direction that magnetic field's going in. So on page 260, you have a quick question to answer. So how do electric currents relate to magnetic fields? And we just gave you a whole bunch of ways how they are. So how do electric currents relate to magnetic fields? Make sure you go ahead and answer that on page 260. Magnetic fields around straight wires. Mrs. Escalay has a typo there. Looped wires, sorry. Might as well fix it, huh? So magnetic fields around looped wires. The direction of the field still depends on the direction of the current, and the field can still be turned on and off, just like the current being turned on and off. But the difference is when you take a wire and you loop it, so you shape it into a loop, you can actually increase the magnetic field inside that loop. So that's one way to increase the magnetic field. Just take that straight wire, make it into a loop. So on page 261, we have a reading check question. You have a straight wire with a current running through it. What effect will looping the wire then have on the magnetic field? What did we just say? If I loop that wire, what is it going to do to the magnetic field? And here's just a great picture showing us that. So on page 261 in the model it, here we have the wire. So it says the overhead view of the magnetic field formed by a current flowing through a single wire is shown. The magnetic field lines are closest together in the center of the loop where the magnetic field is stronger. The number of loops in a wire can control the strength of a magnetic field. So the first thing you need to do is draw the magnetic field lines around the two stacked loops of wire down here on the bottom. And then answer the question, is the strength of the magnetic field inside the loop greater or less than the strength when there was just one loop of wire? So what do you think? One loop versus two loops. If you need to pause the video to do this, then go ahead and pause. Solenoids. People who are car buffs, maybe you have heard of this before because this is a part on our cars. So solenoids and electromagnets. A solenoid is a coil of wire that has a current running through it. If you're a car buff, you've heard of it because it is what is used to help start your car. When these go bad, this may be one of the things that cause your car to not start properly. It's also found in paintball gun mechanisms, and it's also the reason why your doorbell rings is a solenoid. So here's a picture of it on the left-hand side there. So there you see, or the right-hand side is probably a better picture. I just see a coil of wire, and there's a current running through it. If I want to increase the magnetic field it's producing, if I actually increase the number of coils or loops of wire or bring those coils closer together, I will actually increase the magnetic field. So on 262, we have a math toolbox. A scientist conducted an experiment to investigate how different factors affect the strength of a magnetic field in the center of a solenoid. The solenoid was made of iron wire. In the experiment, the scientists changed the current passing through the wire and the number of coils per unit length of solenoid. The result of the experiment are shown in the table. Tesla is the SI unit for the strength of a magnetic field. So if I look at these first numbers here, I have 100 coils per meter, 1 current of amp running through it, and I can see what my magnetic field is, 20,000 Tesla. I'm going to double the number of coils, so I went from 100 to 200. I kept my current the same, but look at what it did to my magnetic field. It doubled my magnetic field. So doubled the coils, doubled the magnetic field. On the bottom, whoops-a-daisy, sorry. On the bottom, so I went from 100 coils to 200 coils. Current is the same again, same gig here. 40,000 went to double it. So based on that information, go ahead and answer the questions on the bottom here. Questions number 1 and 2. If you need to pause the video, pause the video. So electromagnets are really cool. So they are things that we can use to our advantage because sometimes maybe we need a magnet, sometimes we don't. This comes really handy for doors. If I want a door to open, like the doors in the high school now, how we have them, if I want it open, I can run this card in front of it. The magnet will no longer exist. I will be able to open the door up. And electromagnets are very useful in that sense. All right, so let's watch this video on electromagnets.
Hi, this is Ben Finio with Science Buddies, and if you want to know what an electromagnet is and how they work, then this video is for you. You might already know about regular magnets. They have opposite poles that attract, similar poles that repel, and they can even attract other metal objects that don't attract each other, like these paper clips. You can also take a compass, which is itself a small magnet, and move it around near another magnet, and the needle will point in the direction of the magnetic field. So how does a coil of wire manage to behave the same way? It turns out that moving electrical charge, or current, creates a magnetic field. Watch what happens when I connect this piece of wire to a battery. It makes the compass needle move just like a magnet did, so we know the wire must be creating a magnetic field. This magnetic field takes a circular shape around the wire like this. However, the magnetic field around a single straight wire is very weak, not enough to pick up even one of these paper clips. You can make the magnetic field much stronger by wrapping the wire into a coil called a solenoid. This causes the fields around each individual turn of wire to add up to make a much stronger, more uniform magnetic field similar to that of a bar magnet like this. However, you'll see that this coil of wire is still too weak to pick up an individual paperclip. To make an electromagnet really strong, you need to add a ferromagnetic core like this iron bolt. Ferromagnetic materials have many smaller individual magnetic domains. Normally, these domains are aligned randomly and cancel each other out. However, in the presence of an external magnetic field, these domains align with each other and the external field, making the overall field much stronger. Watch what happens when I insert this iron bolt into the core of my electromagnet. Now it's finally strong enough to pick up a paperclip. Unlike a regular magnet, an electromagnet can be turned on and off by removing the flow of electrical current. If you reverse the direction of the electric current, you reverse the direction of the magnetic field. To change the strength of an electromagnet, you can change the number of turns in the coil, the length of the coil, the amount of current flowing through the coil, or the core material, all of which would make a great science project. Because they have very low resistance, the wires in electromagnets can get very hot, so you should always disconnect them when not in use. The paper electromagnet in this video was just for a demonstration, but you should not try this at home because the paper could actually catch on fire. To see a variety of science projects that use electromagnets, as well as instructions for thousands of other science and engineering projects, visit us online at www.sciencebuddies.org.
So electromagnets are simply a solenoid that has some type of a ferromagnetic core inside of it. So that's the difference. So an electromagnet is a solenoid, but it has a ferromagnetic core. So it's going to have either iron, nickel, or cobalt in the middle, like you saw in the video, like he had bolts inside of there that he was using. So if I want to make that a stronger magnet, I'm either going to, just like you saw in the video, increase the number of coils. I'm going to put those coils closer together, or I can also increase the current on those things. So here's a picture showing us what an electromagnet would look like. So we have the nail in the middle, run that electric current through it. It'll turn that nail that normally is not a magnet. It will actually turn it into a magnet. So some doors are locked with electromagnets and can only be unlocked electronically. Just like I said, the ones in the high school are here now. We also have electromagnets that are used to lift trains off of tracks, like we saw earlier in this chapter in the video. And electromagnets can also be used to produce vibrations in earphones. So on page 261, we're going to answer the reading check question: what is the structural difference between a solenoid and an electromagnet? How are they different? All right, so I think we're going to end with, we have another video on electromagnets here.
You might think that magnetism might only matter to 3 kinds of people: physics professors, the refrigerator industry, and insane clown posse fans. But magnetic forces are actually responsible for so many things that we take for granted in modern life, including that sweet gaming rig next to you and that phone in your back pocket. Now, for a long time, electricity and magnetism were thought to be unrelated phenomena. But as our scientific understanding evolved over the years, we found that electricity and magnetism were part of the same fundamental force called, you guessed it, electromagnetism, one of the 4 basic forces that make just about everything in the universe possible. Now, every electric current produces a magnetic field, from the tiny traces on your motherboard to huge high voltage power lines that carry electricity across great distances. But this effect is usually weak enough that it's not obvious or impactful. So when we want to harness magnetism so we can actually do useful stuff with it, the conventional way to achieve this is to loop a wire carrying a current around and around many times in order to concentrate the magnetic field. Then, if you want to get really fancy with a nice strong magnet, you can loop the wire around a magnetic core. Iron is great for this. This is a pretty simple concept, but it forms the basis for many modern electromagnets, making the electromagnetic force an incredibly versatile tool, especially since you can control how strong the magnet is simply by changing the number of turns or coils of wire, or by adjusting how much electricity is flowing through them. But Linus, all I've ever seen electromagnets used for is picking up cars or scrap metal at the junkyard. How's that relevant to me? Well, for starters, that hard drive that's probably clicking away inside your computer right now relies on electromagnets to read and write data. It has tiny little heads that look like the needle arm on a record player that are really just small electromagnets that orient the magnetic domains in the spinning hard drive platter a certain way as it flies past to represent the zeros and ones of data. Though current hard drives rely on thin films rather than conventional coils for writing. Yay, progress. On to another example. What if all that computer use has led to some sort of repetitive strain injury? Well, your doctor might use magnetic resonance imaging, better known as MRI, to have a look at the inside of your hand. This works by using very strong magnetic fields to excite protons in your body, which then actually give off radio waves that can be captured to form an image. And then, when you're done with your imaging and it's time to go home, the ease of varying the strength of an electromagnet, as I mentioned before, has even made travel via maglev train possible. Electromagnetics attached to the bottoms of these trains push the entire train up and forward, allowing them to hover over a metal rail, and in doing so, travel without friction. So thanks to this, the fastest maglev trains today can travel at 270 miles or 430 kilometers per hour, fast enough to rival some turboprop airliners. But even if you've never ridden a maglev or had to stick an appendage in an MRI machine, you've still benefited from electromagnets, as they actually supply nearly all of the world's electricity. Whether most of your country's energy comes from coal, oil, hydroelectric, solar, wind, or nuclear, almost all power plants eventually convert whatever kind of energy source they use into mechanical energy. They use that to drive a turbine, which spins a coil of wire surrounded by a large, powerful, you guessed it, magnet. This causes an electrical current to flow through the wire, which is sent to the electrical grid and ultimately to your house. So while watching this episode of Tech Quickie isn't exactly the same as getting your PhD in physics, hopefully you now understand the fundamentals of electromagnets and how do they work. And you didn't even need to talk to a scientist to do it. Speaking of how they work, you might think that magnets...
All right, I like that video. It goes through a lot of interesting ways that we literally use magnets and kind of how we produce electricity using magnets. So last thing you're going to do on page 264 is the lesson 3 check. Number 1 has to do with that video that we watched right at the beginning. So think about think about the compass near the wire. I think the rest of them we should be good. All right, and that will be everything for topic 6, lesson 3.